Today I'm continuing my evaluation of the SwiftIO system. This is a new development board, a competitor to the Arduino and the likes of the Raspberry Pi. If you haven't seen my first video, take a look at that as it will explain where this is coming from. Today I'm going to introduce you to this Arduino Shield. Spookily, SwiftIO are paying homage to the Arduino in the development of this board, and we can connect various sensors easily using these pre-supplied cables. This shield fits over the SwiftIO board itself, like so, giving you easy access to the programming and the UART ports there. Here are the sensor boards that we're going to be playing with today, just the buzzer, the button, the light sensor and the potentiometer. I am really impressed with the quality of these boards. They really have done an outstanding job. If you compare it to the typical offering that you will find in many Arduino sensor kits, there is really no comparison. Let's move on then and take a look at the sketch and try out some of these sensors. Our first example then in mission 3 is just adding the simple push button module. Again, the board is clearly labelled and marked out with the different analog ports and the digital ports. This port here, you can see on the PCB, is the digital input D11 and D10 and ground and 3.3 volts. For adding other Arduino compatible shields, we have the standard layouts here, and once again all of the pins are clearly marked. On to mission 3 then. If we now plug the download port in and press our little button here, and now here in the IDE we can see the little Swift sign, so the board has been recognized. The push button sketch then, very simple, has a description of how it works here. The input pin going from low to high when the button is pressed. There's a little delay, 50 milliseconds we'll see, between it recognizing the switch to avoid any false triggering caused by the switch bouncing, what's called then debouncing. Here then we've set the LED to red to find the digital input on D10. Here's our 50 millisecond delay, and here's our detection of the button being red. Let's download the sketch then. Message compiling. Our information about the memory used. If we now push the button, we can see on the main board the LED follows the button presses. Let's now then move on to mission 4, where we add the potentiometer. In this example then we're connecting to the analog input and we're connecting a potentiometer. This will be varying its resistance, and that will be measured by the code in the sketch. Here we see the analog input being defined on A0 and the LED set to red. Here then it's reading the A0 input and then toggling the LED on and off, and then just pausing. Let's see it in action then. Download the sketch. And it's been downloaded to the board. We see our red LED blinking at a certain rate. If we now rotate the potentiometer, it's going really fast. That's right at one extreme. As we turn it clockwise, the flashing rate gradually decreases, and at the other end of the potentiometer, there it is at around about half a second, I guess. The coding challenge here, it says, is try and use the photo resistance to have your RGB LED change between multiple colours. Well, that's something a bit different. I thought it was going to say change the speed according to the value of light. That's what I think it means, so that's what I'm going to do. What I've done then is to replace the potentiometer with the light sensor. Effectively, this is a light dependent resistor. We can see the LED blinking at a certain rate. If I now obscure the light sensor, the rate increases. If I cover it completely, it goes to the maximum flash rate, so it looks like it's permanently on. As I uncover it, the blinking rate slows down. It doesn't slow down to the minimum because there's not enough light, so if I now shine my torch on it, You can see now when it's fully illuminated it's at its slowest flash rate. Let's move on now to mission 5. Mission 5 then is using the little buzzer module and controlling the frequency. You can either do this with the potentiometer module, or I've elected to go with the light sensor, maybe more like a sort of theremin. Here then in the sketch we've got A0 again as the analog input. Buzzer frequency is set here. It then reads the value and then uses that value to adjust the frequency, and then it rests for 50 milliseconds. Let's upload that then. Press our button, download. The error that we saw was due to the PWM ID now being changed. In your example then you need to change this to PWM2B. As you may be able to hear, the sketch has been uploaded. I deliberately left the seal on because usually these buzzers are extremely loud and extremely annoying, as you can hear. Now then, if I obscure the light sensor, the tone goes down, and then illuminate it more and the tone goes up. So yes, that is working and really annoying. The coding challenge here is to make the thing play Happy Birthday. Let's see if we can do that. I've modified the sketch to the best of my limited musical ability. The first part is the same, it's just setting the buzzer up, and then the frequencies I've changed to these here, which is a complete travesty of Happy Birthday, but there we go. The way that it's played is that it just takes the frequency count, the number of tones, and then changes them with and then just plays them with a short delay. I know you're dying to hear it. Well, I did say it was nothing like Happy Birthday, but it's my best stab. On to the next mission, I think. The last example today then is just with this little 7-segment display. This may not be terribly exciting, but it's really just proof of concept and to make sure everything's working before we can move on to more complex projects. Looking then at the IDE, it's important that you make sure that your IDE is up to date. If we check up here and about, I'm running version beta 0.11. Previous versions had a problem compiling this. It's advisable to check that. Simply then, it's going to display the number 6, and our challenge after that is to make it spell out the word hello. Let's first make sure that our number 6 is working. Plugging the board in and making sure that we press the button so it's in its download mode, indicated by the green LED here. And in the IDE we see the little Swift icon. We're now in a position then to download, or is it upload? Download the sketch. We get the message building. Before that was compiling, but now it's building. And we see the details of the code and it downloading to the board. The board now reboots and we see our number 6 on the display. Nice and simple. Now then to the challenge of printing out hello. Maybe that should be a challenge for Lionel Richie. How then are we going to go about printing our hello message? Notice here this let 7seg equal 7-segment. The 7-segment is a library that's provided to display the numbers. Let's go take a look at that, which is over here. We can see now what this library or routine is doing. It defines each of the little segments on the 7-segment LED. It defines each one to a specific digital output pin. So here we have the 7 segments and the corresponding digital outputs. What it has then are hexadecimal representations of each of the patterns required to display the numbers not from 0 to 0 but from 0 to 9. If then, as in our sketch, we chose the number 6, it would be going then and activating or turning on the particular digital outputs associated with those segments. However, it's not going to help us initially with our hello message because it only shows numbers from 0 to 9. We're going to have to think how to do this ourselves. Remembering this configuration here, this is what I've worked out. To light the H shape, the equivalent segments need to be lit E, F, G, B and C. Those are represented by digital outputs 4, 2, 3, 7 and 6. If we now translate that into binary, that becomes 0, 1, 1, 1, 0, 1, 1, 0. I was always taught to strike through my zeros so that you don't confuse them with O's. Similarly, I always crossed my 7s even before I moved abroad, which raised a few eyebrows on occasion. Knowing that, then, we then convert that into the hexadecimal equivalent, which is 76. If we then change the hexadecimal value, for example, in the number 6 to 76, we scroll down in the window, you can see that I've done that already. I've uploaded the code and you can see the letter H on the display there. All is good. All we have to do now is to repeat that for E's and L's, and 0 will pass for O, and we should be good to go. I've repeated the exercise then and come up with the value of 79 to represent the character case E. Here in the 7-segment library, I've changed the value in the number 0 location to 79. In that case, here in the sketch, we'll change this value here to 0, put our board into download mode and download the new sketch. Here we can see the values in the download, board rebooting. But what's this? We're missing a segment. We're missing the segment A at the top there, which is digital output 8. What's going on? Do we have a faulty display or is there something else? This is what we need to investigate. Brought out my logic probe to find out what's going on here. On the 7-segment display, the first pin is 3.3 volts, so we have a high there. If I touch ground, we get a low. The next pin is D2, which is low, so that is correct. That's driving the 7-segment display, so D2, that's correct. D3, yes. D4, yes. D5, yes. D6 is not being driven because it's not being lit, so it's high, which is correct. D7, correct. D8, nothing. What's going on there? Now these pins will be connected via a current limiting resistor to the corresponding digital outputs over here. Let's then find a piece of wire and put that in digital output 8, and we can see that digital output 8 is in fact low. Therefore there appears to be a problem with the connection between the D8 pin here and a corresponding connection on the 7-segment display. Let's take a closer look at the hardware. Disconnecting the power, gently easing the board off. Okay, let's take a look underneath the 7-segment display, and having a well-trained eye, I can see the problem immediately. It probably isn't obvious to everybody. I will put this under the microscope, but there is a component missing. These little guys here are the current limiting resistors for the LEDs in the 7-segment array, and there is one missing. These will probably be around 330 ohms. Under the microscope then it's easier to see the surface mount resistors and the one which is missing on D8. I don't think I have the surface mount varieties, but I will solder an equivalent resistor in place and then we will test. I don't have the surface mount, but this is 330 ohms, 5%. There we have it then, functional if not aesthetically pleasing. The moment of truth then. And there we have it, a complete E, another result. Now I could go on with the L's, etc., but I think this video has gone on long enough, and another project is calling my attention. I hope you found that of at least some interest. Cheerio.